This episode of Vermont Rocks with John, Kim, and Julia Boyles begins at the Berlin Park and Ride. We'll be traveling north from Exit 7 to Exit 16. Along the way, we'll take geology moments at the Waterbury Rest Area and the Williston Rest Area. This podcast is divided into chapters so you can follow along as you drive.
The purpose of this trip is to take you on a trip through a cut of the earth for 40 plus miles. Rocks that range from 550 million years ago to the glaciations ending at 11,000. I'm John Kim, I'm the Acting State Geologist. I've been doing Vermont geology for 25 years and been making geologic maps, bedrock geologic maps over that whole time. I've worked for the Vermont Geological Survey, which is part of the Vermont Department of Environmental Conservation, where we use geology to solve applied geologic problems or environmental problems, such as work with groundwater contamination, where we can find groundwater. We work with landslides. Where are they happening? Why are they happening? We work with any of our clients, which includes Vermonters and state agencies, to try and solve those problems. Well, I've been in this since the summer of 1980, when I spent 12 weeks in the field at Colgate University studying field geology, which was required. I've been a passionate geologist, and I think learning about all these detailed geology concepts, you know, and when many people look in at what we're studying, they may think that, oh, this is such amazing detail and too complex. But we have found over the years that all of these detailed geologic concepts apply directly to solving these applied geologic problems. For example, we've used these concepts to look at groundwater contamination in Bennington, groundwater contamination at the Rutland Airport. We're using these concepts in general to look at how landslides change over time. So we're looking at the Earth as a whole to try and develop a three-dimensional framework to solve these problems. And these geologic disciplines are all just critical to understanding. When we get on the highway and you see the rocks on the outcrops on the side of the interstate, you'll notice that they're not horizontal, they're all standing on end. And they're standing on end because of basically two major mountain building events that folded and faulted these rocks. And so instead of being horizontal, they're now various stages of nearly vertical or between vertical and horizontal. One thing to point out is what we're looking at on our transect. The general theme is as we go from entering onto the Berlin entrance, we're going to be starting with generally the youngest rocks. And I think you need to think about, as we go west, the rocks are a series of slices that are on top of one another, with the youngest ones on the east and the generally oldest ones on the west. And they're stacked on each other as these huge, thick, what we call thrust slices. And so as you go to the west, we're going for what's called structurally highest, the rocks that are youngest and are on top, to the rocks that are oldest as we go towards Lake Champlain. The Earth is approximately 4,500 million years old. Earth's history can be divided into different time descriptors. The eons is that we're going from the Precambrian to the Phanerozoic. And the Precambrian runs from about the age of the Earth to 540 million years ago. That's the Precambrian. Then from 540 to the present is essentially the Phanerozoic. But then we subdivide. We take the Phanerozoic eon and we divide that into sub-eras. And the eras are from the oldest, the Paleozoic, then the Mesozoic, and then the Cenozoic. And from those eras, we divide into periods. And the periods are really what we're going to be talking about, which would be, I won't give them all, but starting with the Cambrian at 544, going up through the Ordovician, the Silurian, the Devonian, and then essentially all the way up through the Cretaceous, which is the top of the Mesozoic. So I took you from the Paleozoic to the Mesozoic. And then we need to really fast forward from there to 1.8 million years ago to approximately 11,000 years ago, which is the last glacial essentially events, with the Wisconsin glaciation, named after Wisconsin, running from about 75,000 years ago to 11,000. Vermont's geologic history ranges from about 1,400 million years to the present. And what we'll be seeing on the trip is generally from the about 400 million years ago to the last glacial episode about, say, 10,000 years ago. We are in terms of these belts or slices of rocks, we are in what's called the Connecticut Valley Belt or Slice. This is from a younger ocean basin, which was about between 420 and around 400 million years old. And the rocks we see on the side of the road are these gray, we call them phyllites. Phyllites are metamorphic rocks in which you have changed a shale by temperature and pressure of these mound building events into a phyllite. And we had what we call dirty limestones or sandy limestones that were turned into what we call sandy marbles. And you can look along the side of the road, and remember, you're looking at these rocks from this younger, in quotation marks, ocean basin, and they're basically standing on end. And so we know that they weren't deposited that way, because we know from a simple geologic rule, the law of original horizontality, that the sediments are basically deposited horizontally. And yet here, because of the second mountain building event, the younger one, the Acadian mountain building event in the Devonian period, we actually look, and if you look on the right, you see steeply dipping, rusty weathering phyllites, which were once shales in this younger mountain basin, standing on end. And as we come down into the valley towards Route 2 exit, we're going across a fault, and we're going across the Dog River Fault Zone. And there's a big age difference between the rocks on the right first that are gray, which is the Waits River Formation of the younger ocean basin, now are into the Stowe-Moortown slice of the older ocean basin. So we've gone from the younger ocean basin across a major fault that runs a considerable distance north and south, and now what we're in is called the Moortown Formation, from which this slice is named. And what you also see is that the rocks here are these green, we call them phyllitic or shaly quartzites, and they're also standing on end from folding faulting. Now the rocks of the Moortown Formation are as old as 500 million years old, perhaps between 480 and 500 million years ago. And research in the last 5 years or so has showed that tiny little minerals in the Moortown Formation give a fingerprint that the Moortown Formation came from way across this old ocean basin that I'm talking about. Remember, the second ocean basin way to the east, and was pasted on to what was then ancestral North America during the older mountain building event, the Taconian orogeny in the Ordovician. And things to see, you're going to see a lot of Morton. The Morton is formations are named after the town or geographic location where they were first described by geologists. So this Morton formation was first described by geologists officially in Morton, Vermont. And so you see that it's basically a grayish green, it's a shaly quartzite. It's pinstriped in that it actually has alternating layers of platy minerals, micas, chlorite, and muscovite, and then lighter colored, light gray layers of quartz. And so if you can imagine this, we're going through a Morton where it's very thick. So this is going to go all the way into, we get just past or around the Middlesex exit, where we will change from the Morton formation across a fault to, we're still going to be in this what we call the Stowe-Morton slice overall, and we're going to go into what we've mapped and has long been called the Worcester Mountains, which themselves are a slice that are bounded on the west and east side by faults. The beautiful Worcester Mountains that go 20 miles from Waterbury all the way to Morrisville, Vermont. So those are all a slice tucked in beneath this Morton slice. So one of the things, and we'll develop this more as we go along, is that if you look at the rocks standing on end, the interstate was constructed virtually perpendicular at right angles to the rock layers that are standing on end. And the reason this was easier to do, or easier to blast this way, is the same reason that the Winooski River cuts completely across this major bedrock structure, which is running essentially north-south and standing on end. But there's actually a Mesozoic, remember we're talking about, and I'll put the Cretaceous period in the Mesozoic era. We had zones of cracks or fractures develop all around the northeast, and the Winooski River is following in general from Montpelier towards Lake Champlain a well-developed fracture zone from the Mesozoic that's superimposed on top of these Ordovician and Devonian and older rocks and structures, so that it was actually easier for the Winooski to cut across this fracture zone because it was a zone of weakness. And so the engineers were also able to use, to a large extent, this weakness, this rough east-west weakness, to blast the interstate. And so evidently the interstate was an amazing engineering project at the time. The interstate's construction, countrywide was starting around the 60s, and it, I think it was not completed for Interstate 91 until actually the late 70s to early 80s. And and for Exit 9, now we've actually crossed out of what's called the Morton Formation, and we're going to go into a big outcrop, or a big outcropping ledges of rock on the east side, or I'm sorry, the north side soon, and these will be rocks of the Stowe Formation. So these rocks, to a non-geologist, you think, oh my gosh, they're green, they're brown, they're gray, they look all the same. But to geologists with a lens and often thin slices of rock that you can look at with a high-powered microscope, or even doing some chemical analysis, these rocks are actually quite different. And so as we come up here, we're actually coming to what we call the Stowe Formation. Again, this is actually a sliver or slice of Stowe in our cross-section going to the west, and you'll see it coming up on the right about a half mile ahead. This is actually a greenish gray, also a phyllite. Remember, we take a shale, we metamorphose it first, it becomes a slate. We metamorphose it more, it becomes a phyllite. We metamorphose it more, it becomes a schist. So this is actually the Stowe Formation. So as we're going along, we've just taken from the Waits River Formation, essentially to the Moortown Formation, now into the Stowe Formation, everything's standing on end as a result of folding and faulting during these two major mountain building events. The rocks on the Berlin side that were east of Montpelier were the Silurian to Devonian rocks that only experienced the second Devonian mountain building event or orogeny. And now we're into the older rocks, which experienced both the older mountain building event in the Ordovician period at about 450-ish million years ago, and also have significant effects of the second Devonian mountain building event at, say, about 380 million years ago. So as we come through these rocks, we're still in Stowe Formation rocks, and we're about to come into ancient volcanic rocks. And you'll see them as this deep green coming up on the left. By greenstones, these are mafic or dark-colored metamorphosed volcanic rocks that were associated with the mid to late stages of opening of the older ocean basin that we are driving through slivers of as we head west towards Burlington. That's the only spot where we'll see those, but think about those. We're actually probably about 500 million year old volcanic rocks that were metamorphosed by temperature and pressure elevations during the mainly during the older mountain building event.
So we're about to hit Bolton Exit 10.
So now you're going to notice the change from, remember, we were in mostly green rocks and rusty rocks, and now we're starting to see, and gray rocks, where now you're going to actually start to see rusty weathering black rocks. And these are the rocks of the Ottaquiche Formation that we'll start to see soon on both sides of the road, but we're going to start to see them as we start downhill into Exit 10. And all around, we'll keep going to the Waterbury Rest Area. Nope, keep going, keep going.
So we're crossing Exit 10.
So here now, we're actually now into the next rock formation, standing on its end to the west. We've gone from the Moortown to the Stowe Formation, and now we're in the Ottaquiche Formation. Rusty weathering black phyllites and quartzites. So these were black shales and quartzitic rocks, basically sandstones. So shales and sandstones in the ocean basin. And as we continue to the west, those rocks, which were all around the Exit 10 interchange, now go back into Stowe Formation rocks, and then we're actually going to have covered, which faults often are because they are zones of weakness that are easy to erode. But before we go, we started in what we're calling the Connecticut Valley belt or slice. We went into the Stowe Moortown slice, and now we've come out of it, and we're actually in the Green Mountain slice. Look at all these rusty weathering rocks. These are the Hazen's Notch Formation. These are rusty weathering rocks that contain black feldspars, which are really conspicuous and distinguish it from others, those other formations we've seen. And we also are looking at some of these green phyllites and now schists of the what we call the Facein Formation, which is basically a green schist that also often has these conspicuous white feldspars that help us distinguish these formations. So we've gone through quite a bit just in the basically 13 miles from when we got on in Berlin through Waterbury, and we're going to take a geology moment at the next parking area, which is on the right. So it's right here, Julie. So we're still in the Hazen's Notch Formation of the Green Mountain Slice. The Hazen's Notch Formation makes up a large portion of the Green Mountains, and the Green Mountains are the slice itself was formed into what we call an anticlinorium or anticline, which is a giant upfold, and that occurred as a result of the second mountain building event, the Acadian event, say in about 380-ish million years ago. Now, one of the things to point out about the mountains in Vermont and New England in general is that they are an erosional mountain range, okay? We are looking at basically mostly the contrast in ease of erosion for the mountains versus the valleys. So with the mountains being more erosion resistant rocks and the valleys being more rocks that are easy to erode. And in addition to that, there are these large upfold and downfold structures that are providing some influence, but basically we're looking at a mature landscape, which is mainly a result of erosion. And the last tectonic events to affect this area, arguably, were about 80 to 100 million years ago. And so this landscape has evolved over time with erosion to the present. And then we had a significant sculpting and accentuation of the topography during the glaciations that took place between 1.8 million years ago and 11,000 years ago. As you look to the southwest, you're going to see the top of Camel's Hump, one of the 4,000-foot mountains in Vermont. And you see that it has a very unique shape. It's basically one camel's hump. And what's important in terms of the overall sculpting of the landscape is if you look how conspicuous the gentle slope on the north, or if we're looking now at the right side of it, is from the very steep slope on the south side. And pardon my French, which isn't very good, but that feature is called a roche moutonnées. Essentially, the steep south side reflects the fact that as the ice, the glacial ice, think about the ice which was a mile or more thick, as it was moving south, because we had a particularly cold climate and lots of snowfall in the north, making these very thick ice sheets, and they actually moved south because ice, although it's really hard when you fall on it when you're skating, playing hockey or figure skating, ice actually deforms plastically. And so the shape of Camel's Hump is due to the fact that ice ramped up the south end side, making that gentler bedrock ramp, and then tore off the bedrock on the south side, making the very steep side. If you're a hiker and you hike up Camel's Hump, you have two different options. You can come up from the sides or you can come up from the end. If you come up from the sides, you will generally follow some switchbacks and follow, gently or to crossing contours. If you take the long trail up from the south side, you'll be pulling yourself up with your hands on a very nearly vertical slope. And when you get to the top, you will be exhausted, and people that came up from the sides will be laughing and having picnics. And so that glaciation was responsible, the last glaciation, the Wisconsin glaciation, was responsible for generating the shape of Camel's Hump. And it's not just Camel's Hump. If you look all over the state of Vermont, you'll see asymmetric mountain ridges with a more gentle north side and a steep south side. That's from the southward migrating ice ramping up from the north and tearing off parts of the south to make that asymmetric shape. When we started, we were in what we call the Connecticut Valley Belt, and the mountains there were very steep and generally lower of elevation and shorter. As we crossed into the Stowe-Moortown slice, we were starting to see, instead of being more isolated short peaks, we're starting to see longer continuous ridges. And now that we're in the what I call the Green Mountain Belt, we're in what are long continuous ridges that go all the way up into and through Quebec and all the way down basically towards Long Island Sound, which are the rocks of the Green Mountains that become the Sutton Notre Dame Mountains in Quebec and become the Berkshire Mountains in essentially Massachusetts generally. And so we've gone from the topography being the short, steep mountains in the Connecticut Valley Belt, the slice, and then started to go in the Stowe-Moortown Belt into more elongate ridges, and then the Green Mountain Belt is just continuous ridges. And then when we end up, we're going to drop down off these Green Mountain slice rocks into those of the Champlain Valley, which is mostly weakly metamorphosed limestones and shale that erode very easily, in which case then we're just going to have generally rolling topography with isolated areas like Mount Philo, Pease Mountain, Snake Mountain, where more erosion-resistant rocks, which were once sandstones, are now considered quartzites, are standing high because they are harder to erode. So if you've been driving in Vermont for very long, this particular portion of Route I89, as you go downhill essentially towards Bolton and along 89, we get down to a place where this hill levels out, and it's called Bolton Flats. So if there's heavy snows, this is white knuckle terrain. And the reason is that in this particular Bolton Flats area, black ice seems to develop more often than in other stretches of the I-89 interstate. And one of the things to think about, I'm not a climatologist, but if you start to think about, if you come down this hill, you're coming down a pretty steep hill for 2 miles into the flat Winooski River Valley. And then a couple miles ahead, you're going to come out of it going towards Richmond. So you're in actually, the I-89 drops down into a basin along the Winooski River. And when I've ridden my bike in here, the winds are often swirling and things like that. So not that I'm an expert in this, but it seems like this basin is some way for winds to change and interact with the road surface and cause more black ice than in other parts.
Now we're gonna pull out of this rest area, and so if you're listening to this as you're driving along, you may want to hit the road again.
So yeah, one thing to point out about the Green Mountains, essentially the Green Mountains represent the highest mountains in Vermont, the ones that are all over 4,000 feet are in the Green Mountains. And not uncoincidentally, many of the major ski areas in Vermont are in the Green Mountains because they form the highest long continuous ridges and are very amenable to putting in pretty long lifts and having pretty long runs. So there's a reason why the ski areas are where they are. Now we're descending down. Again, we're heading basically northwestward along 89, and we're dropping down this hill, which is about 2 miles, into the Bolton Flats area or Bolton area of Vermont. One thing to have a look at least have your passenger have a look at, is on the right side, you're going to start to see these really big outcrops of Hazen's Notch Formation. Remember, we're part of the Green Mountain Slice. We keep going down to lower structural levels in this pile of slices as we're going to the west. One thing to look at here on the right is look at the layers. The layers are not straight. What you're going to see is squiggles in the layers. And you're seeing that the layers are actually squiggling up and up and up. If you can see there, especially when you're even with it. So you see that the layers are squiggling up. They're climbing on one side of this big fold. They're still climbing. And then we're going to have another really big outcrop or ledge on the right. And you'll see that they're still climbing. So this is part of that Devonian Green Mountain Anticlinorium or arch structure that is so distinctive, that goes all the way up through Quebec and all the way down towards Long Island Sound. And so here is another outcrop of it. These are rusting weathering Hazen's Notch rocks. And then look right here, you're seeing that they're climbing up. And not that you have to continue with such detail, but one of the things to think about is that once the rocks climb so far in a fold, they actually may come down and not be climbing, maybe going kind of what we call neutral, and then they actually may start going down and then going up. And if you were to ride this stretch of Route 2 along your bike or going slower in a car, you would see those variations. So we had those big ledges where the folds, the Green Mountain folds, these ones that are about Devonian in age, were climbing. Here they're still climbing, going this way. Some of these outcrops ahead, and you won't be able to see this from your car, but I just want you to think about it conceptually, that you're looking down at different parts of the fold that are not climbing as steeply towards the west. One of the things about this, and you have to get a look at the new Vermont state map from 2011. We have them on our website, and you can actually buy them. We're down in what's called the Bolton window. And so a geologic window is when you're able, because of erosion, able to look down at deeper structures or slices in this whole pile of thrust slices this is from the first older mound building event in the Ordovician, and you can actually look down at slices that are below. In this area that was mapped by Peter Thompson in the 1990s and his wife Thelma, they found that there's actually marble layers, so metamorphosed limestone layers in these hills that actually have fossils in them. And the fossils are called conodonts. And the conodonts are actually ancient organisms. I think there's some debate about exactly what they were, but these are composed of their chitin, which is basically their shell, and it's made of phosphate. And the phosphate is very, very difficult to erode, and therefore they're preserved. And these fossils dated those various limestone or marble layers at about 460 million years ago. So this was really a surprise to find fossils in these rocks that are, that range in age from probably could be as low as 500 to in the mid 400s. So that was a great find, and these were analyzed by the U.S. Geological Survey in their Virginia office. So we're all passing through that, essentially that Bolton, what we're calling the window, and we've just passed the area where, or are just coming to the end of the area as you look at the Bolton Village to the left, where the icy roads become much less of a hazard. Once again, what we're doing is if you look up to your left, and this would be the southwest, you see an airline beacon right there? That airline beacon is what all the jets use approaching from the south to Burlington International Airport. That beacon sits up on what's called Honey Hollow. Honey Hollow is actually, when you think of a hollow is generally like a valley versus a ridge. And the hollow is actually the site or the location of the Honey Hollow Fault. And that's how we go from, if you look up to the left, and when we get to just the other side, we're gonna see the second ridge to our left. The Honey Hollow Fault, which we won't see from the road, will abruptly transition us, and remember, we're still in what we call the Green Mountain Slice, but to a different, we'll call sub-slice of the Green Mountain Slice, which is called the Underhill Slice. And these rocks, to people that aren't geologists, they would think that these are very similar to the rocks in to the east in what I was calling the main part of the Green Mountains, and they are. But there are parts of this particular slice where the rocks are somewhat older. And so now we're still in the Green Mountain Slice. I think this is a very thick slice, but each of these slices, and I know I'm making this complicated deliberately, but in each individual slice may be composed of smaller sub-slices. And look here again, we're looking at rocks that are nearly layers, and these are not necessarily beds in the rocks that deposit. These are, remember I was talking about, with metamorphism, one thing you develop through folding and faulting is a foliation, which is an alignment generally of mica or flat mineral grains. And you see as we come through this big hall of outcrops that the rocks, these gray schists and green schists, are nearly vertical. Remember, that's a result of the composite superposition of the older mountain building event in the Ordovician period and the younger mountain building event in the Devonian period. To point out, look here, we're driving 74.4, and we're driving along a particularly straight stretch of 89 in this valley between Waterbury and Richmond. One thing to look at how wide the valley is. The valley is really wide. Remember, we have some structural control of Mesozoic fractures that control the general direction of the valley, but also the glacial lakes, Glacial Lake Winooski, filled this valley with hundreds of feet of ice-cold water back in around 14,000 years ago. So what was a bedrock feature, that these zones of cracks that allowed essentially the ancient Winooski and the present Winooski essentially to cut through the mountain structure. We also have a well-developed glacial lake plain that later evolved into the current Winooski River floodplain. But on the floor of this Winooski Valley, there are what we call varved clays, which are clays in these glacial lakes where there are alternating sandy layers from when the glacial lake was not frozen during the summer to really muddy layers when the glacial lake was frozen in the winter. And so when the glacial lake is not frozen, wind energy can move larger grain particles like sand around. So each one of these varves, which is a winter clay layer and a summer sandy layer, represents a year. And we have a colleague, Stephen Wright from University of Vermont, who has counted varves in this part of Vermont and has gone up to, I think, as many as 300 in a given site. So these glacial lakes were around for hundreds of years, and on the margins of these glacial lakes were beaches, and the beaches were all sand. And so while driving along 89, you may actually see current and old sand pits that represent excavations of these glacial lake beach deposits for construction materials. You'll also see, and we won't see them along here, but you'll also tend to have gravel pits that are along the margins of these valleys, and the gravel pits are called cames. And or came moraines, and these are a result of when the glacier was melting, the meltwater was riding between the glacier and the valley and along the valley walls and moving the sand and gravel around and rounding it and making sedimentary deposits that are our current sand and gravel deposits. So at the Richmond exit, remember we last, and I couldn't show you the fault, and it's going to be the same here, but just as we start to climb up French Hill, going west of Richmond, the very steep hill, you're gonna actually see on just before the Route 2 bridge a Caterpillar sales facility, and just about right in there is where a second fault called the Brome Underhill Fault separates this slice of the Green Mountain slice, remember multiple slices in here, from the next part of the Green Mountain slice. But this particular part of the Green Mountain slice is much more distinctive than the other slices that we showed you. This is now we're out of the Hazen's Notch and Facein formations of the Green Mountain slice. We're out of the Underhill formations and the Facein and equivalents in the next part of the second part of the Green Mountain slice. We're in the Pinnacle Formation. The Pinnacle Formation is the oldest formation along our interstate transect. The Pinnacle Formation dates back to the opening of the Iapetus Ocean. So this is actually, think about the current Atlantic. It's at least 3 oceans before the Atlantic opened. This ocean opened about 570-ish million years ago when a supercontinent called Rodinia rifted apart through stages like you would see in the East African Rift, developing then to a Red Sea stage, and then finally into a main ocean Atlantic stage. So these rocks right here, as we go west, are representing some of those oldest rocks in our transect. And once again, look, they're standing on end. The original horizontality of these rocks, when they were deposited as beds, have been completely disrupted by folding and faulting, development of foliations, which is from the pressure and temperature increases. This is also from the earlier Ordovician and the later Akkadian mountain building event in the Devonian period. So as we continue to the west, we're about to take a geo-moment break at the rest area in 1 mile. So what I want to point out to you is that we're about to go off the Green Mountain slice completely. And by stopping at this rest area, we'll be at the last westernmost extent of the Green Mountain slice, which includes the Pinnacle Formation, what we saw coming up French Hill just previously, and the Fairfield Pond Formation, which is, again, this is a silvery green, was once a shaly sandstone. Now we call it a philitic or shaly quartzite. And we're going to stop and look and talk a little bit at the rest area before we begin our drop into the Champlain Valley and across the Heinsberg Thrust Fault, a major thrust fault, and we'll talk about that a little bit on the way once we resume our drive. Okay, we started. If you think about what we talked about, is that we're looking at a series of rock or thrust slices that are basically standing on end, and the slices are generally getting older and deeper as we go from east to west. We started with the youngest rocks of the Connecticut Valley belt at Berlin, at Montpelier. We crossed into the next slice below, the Stowe-Moortown slice, which also include the Black Ottaquiche rocks at the Waterbury Exit. By the time we got to the Waterbury Rest Area, the small rest area, we had crossed into the Green Mountain Slice, going across a major fault, which much farther to the north is actually the Prospect Rock Fault. And then we stayed in the Green Mountain general slice for quite a while. So since about just before the Waterbury Rest Area until now in Williston. Remember, we started out with the Green Mountain Slice first, which was in the main Green Mountains. I was talking about the anticlinorium, the big arching, which affected all these Green Mountain slices. And then we went into a different slice across the Honey Hollow Fault. Remember, I was talking about the Honey Hollow aircraft beacon? And then we went across the Brome Underhill Thrust right at just on the west side of Richmond. And now we're into the last Green Mountain slice, part of the Green Mountain Slice, these sub-slices, which is the Pinnacle and the Fairfield Pond formations. And we're soon to go over the surface expression of the Heinsberg Thrust Fault as we go down towards your favorite shopping place at Williston and Taft Corners.
We're here at the Williston Rest Area, and Julia, you're going to give us a little history of glacial effects on Vermont.
My name is Julia Boyles. I'm a geologist at the Vermont Geological Survey. Work with John Kim. I started in 2019. I am looking at a map right now that was compiled by George Springston of Norwich University, Stephen Wright of UVM, and John Van Hoosen, who on the ground mapped these surficial deposits. And I'm looking at this map of glacial lakes and the Champlain Sea in Vermont. So at one point in our geologic history during the last glaciation, at various points throughout the ice advance and retreat, ice dammed up major river valleys like the Winooski, the Lamoille, etc. And they created these very, very deep, several hundred feet deep glacial lakes. And as John mentioned earlier, this is when we had the deposition of these varved silts and sands that we can count by years. And the reason that we were able to deposit those really fine silt and clay particles is because when these very deep glacial lakes iced over in the winter, we had very still water, and you're able to deposit these very, very fine particles out of them. So we can go around these areas in these river valleys and actually today map the extent, and we can find these varves and understand these deposits had to have come from an area of very still deep water. So there must have been not a river but a lake here. And then as the ice retreated back to the north, we had various drainings of one lake that would move into a different lake, and we had at one point the Champlain Sea, which was not a freshwater lake, but it was a saltwater, kind of like a saltwater sea, and that's when we have a lot of fossils appearing in the fossil record in that time, and we can identify things from that period. And then before that, we had Glacial Lake Vermont, which occupied an even bigger area. And now that we see today is our modern river valleys and Lake Champlain. Like the Earth's crust is sitting on the Earth's mantle, which is like, think about it like molasses, but really cold. So it's like you put something on it and it'll very slowly sort of mush out of the way. And that's what the glacier did. It just sort of sunk it down slowly, and then as the glaciers retreated, it raised it up slowly. The surficial geologic materials in Vermont, which were deposited, as John said, during the Wisconsin glaciation. So these are all of the materials that we'll see again on the Earth's surface that are not the bedrock. And then in the upland areas, we have what we call glacial till, which is sort of a bunch of jumbled up poorly sorted material like boulders and gravels and sands, and all kind of mixed and melded together in this clay or silty matrix, as we call it. These are usually kind of near the uplands as the glacier sort of scoured over the surface and advanced. It would kind of mush up everything and drop it there. And then in other areas, like in the river valleys, we may have had different like ice contact deposits, or as we were talking about, the lake deposits. So the glacial deposits are very different than the bedrock that we would see. But they're all sort of together on the Earth's surface, but very, very different time periods. So these are happening in a much more recent history, several thousand years ago, instead of millions, several hundreds of millions.
The reason there's a Champlain Sea is that because we had more than a mile of ice over northeastern North America and midwestern North America, the crust of the Earth was depressed. And because the crust of Earth was depressed by that huge weight, the areas up to the north were more depressed because the ice was last there, and therefore seawater was able to come up the St. Lawrence Valley and essentially down what's now the Richelieu River Valley and into Lake Champlain, and then take over a freshwater glacial lake with these seawater and this is roughly in the 11,000 to 10,000 year range. And as Julie mentioned, the reason we know is because of fossils. But one of the most important finds was in Charlotte, when the railroad workers in the 40s found a beluga whale skeleton along the railroad. And the beluga whale skeleton is approximately 200 feet in elevation above the current elevation of Lake Champlain. So we knew, or they knew, that there had to have been seawater there. And that was something that just absolutely flabbergasted me when I first found out about it 25 years ago. So this is the only spot we're going to see the Adirondacks, and it's just going to be for seconds. But if you look at the distant ridges, that's the Adirondack Mountains, the high peaks, and the Adirondack Mountains are also from the Precambrian eon. The rocks over there range from, I think, about 1,000 to 1,400 million years ago, but they were actually exhumed or brought up or domed between 60 and 80 million years ago by some sort of thermal forces from below. But we won't see the Adirondacks anymore after we get down to Williston and the Taft Corners. But just to think about that, over in New York, that's where the old rocks are popping up as the Adirondack Dome. So right now you're actually have dropped down off the Green Mountain Slice, gone over the Heinsberg Thrust Fault, and you've gone into below into these shaly and limestone beds that you can't see across the median, and it's very difficult to see. But if you can look up to the hills to your kind of left and back left, there are homes that are high up on the slopes above the Heinsberg Thrust, and some of these folks were actually able to drill wells from being hundreds of feet above the, or even 1,000 feet above the Heinsberg Thrust in places, and go through it to get water. So now we're actually in the Champlain Valley Belt. This is the lowest structural level, so we're on the bottom of all these different slices that we've gone through from the beginning. And as we get up towards that overpass, you're going to start to see some of these nice banded limestones. Now, these really aren't true metamorphic rocks. We call these weakly metamorphosed sedimentary rocks. Yeah, so that's a limestone quarry that's used to make crushed rock for various construction purposes. And that actually is in the Bascom limestone, which is actually a middle Ordovician limestone. Now remember, what we're on here, the Champlain Valley, or the Champlain Valley Belt or Slice, are rocks that were on the continental margin of this ancient continent called Rodinia. And that these are rocks that were deposited when Burlington was actually 20 degrees south of the equator, and things were pretty darn tropical, depositing limestones and their cousins, dolostones, which is a limestone which has essentially been pickled in fluids with magnesium. But here on the right, you're going to see various limestones that are part of this Champlain Valley slice. And up ahead, we're going to actually go into rocks that are older than this, because we're going to be winding up and down in elevation. There's banded limestone of the Bascom Formation. So we're in the Champlain Valley. This is the lowest slice structurally from once we started, and all the rocks to our east were essentially pushed to the west over these rocks, either Great Mount in the Ordovician-Taconian orogeny, or to a lesser or negligible mount in the Devonian orogeny. So here we're approaching the 189 spur of 89 into Shelburne Road and Route 7, and the speed limit drops, and we're going to actually not have much outcrop for a while. So if you think about, and this is all in current coordinates as of this year, think about a line connecting roughly Burlington to Albany, up to just east of Montreal, and up to just west of Quebec City. That was actually the margin of this ancient, the continent at that time was called Laurentia, which split off from Rodinia. But all these tropical sediments and the rocks that form from them were deposited in basically tropical to subtropical ocean, with this case the Iapetus Ocean, when this whole landmass was south of the equator. And so not only do things collide in map XY space, or XYZ, with Z being elevation space, but also the whole concept of plate tectonics is that thin crustal plates are moving on essentially a upper mantle, and are moving as jigsaw pieces over the Earth's history of millions of years, and end up going thousands of miles over time. And this is where the concept of deep time, millions of years, meets the concept of really large distances. So anyway, this Burlington was a neat place to be, between let's just say the kind of the lower Cambrian period and up through the Ordovician. Now we saw that we drove along the Winooski for a long way, and then we kind of veered off from it, because the Winooski actually took a bend to the north around Williston, then cut back to the west. But here along the Winooski exit, Essex Junction exit, you can actually look into the Winooski River. Remember, so this is the same river, but look at the bedrock control on the river, which forces the river where to go. And this is all the Clarendon Springs Formation, the uppermost Cambrian period. And there you see actually a power hydroelectric dam using one of the drops along the river. And so here's a perfect example for this story. We are going past the Winooski exit onto Route 15. And remember, I said that rock formations are named after geographic features, often towns where they were first described. And as we get up towards this Winooski Colchester exit, you'll actually start to see, or actually the entrance, this is just beyond that, you'll also start to see this cream-colored to tan, weathering, really well-bedded dolostone. Remember I said a dolostone is a limestone. that has actually been exposed to magnesium-rich fluids at some time in its history and changes the limestone, which is calcium carbonate, to calcium magnesium carbonate. And so here's the Winooski Colchester exit, and if you were to get off here, you would see this dolostone I'm talking about. But as we go around and look at the exit ramp, you'll see it exactly on the right. So this is actually a limestone, a bedded limestone. We're looking at the original beds in the limestone as opposed to a foliation caused by the pressures and temperatures of mountain building events. And here on the right is exactly what geologists describe as the Winooski Formation. So we've gone across the Heinsberg Thrust where things were, the Heinsberg Thrust is only dipping, because we couldn't see it, is only dipping 10 to 15 degrees, right? So all the rock slices above it seem to have much steeper dips. So that last part of the Green Mountain slice has generally steeper dips to the east. And one thing to notice, so now we're below the Heinsberg Thrust, and we're on to what we call the Champlain Valley Slice. But the Champlain Valley Slice is actually divided also. So now we're below the Heinsberg Thrust, but we're above the Champlain Thrust, which is right on the Lake Champlain shoreline. You all know it from looking north to Lone Rock Point from North Beach. You'll also know it if you hike Mount Philo, Mount Peace, Snake Mountain, Buck Mountain. So that thrust fault, they just don't end. They go long distances. And in particular, the Champlain Thrust goes down to about Rutland and then cuts across into New York State, where it goes for quite a ways. It continues up into northern Vermont, where it changes names at the Quebec border into, I think, the Phillipsburg Thrust. But anyway, so it's now we're down at the lowest and essentially part of our whole drive in terms of being the lowest slice of rock. Now we're looking at the brick red Moncton Formation. This is a sandstone deposited right near the beach. If you go to Salmon Hole over near UVM, in this you'll see burrows by worms, horizontal and vertical. You'll see ripples. You'll see mud cracks, which means that the sediment was exposed above the water-air interface for periods of time, say at low tides. We call them neap tides. So this is a shallow water sandstone. The Winooski Formation, which is the dolostone, is actually younger than this and is on top of this, but because the interstate is, you see, we're going down and up and down and up. And in addition to going up and down in terms of younger to older parts, going from the Moncton to the Winooski, these rocks are also folded broadly. So the folds are also influencing what you see. So here is more Moncton Formation. The Moncton Formation is at the Champlain Thrust Fault from around about Shelburne Point, going south to Pease Mountain, Philo Mountain, Buck Mountain, Shell House Mountain, and Snake Mountain. But as you go north from Shelburne Point, where there's the Moncton at the Champlain Thrust, it goes into the Dunham Formation, which is also a dolostone, but the Dunham Formation is older than the Moncton Formation. So what happens is there's some sort of ramp going from Shelburne Point to Lone Rock Point, where you're actually you're basically the older Dunham Formation is reappearing. Yeah, so what we're going to do here is we're going to be wandering up and down, and remember these rocks here are dipping about 10 degrees or so about to the east. That dip reflects the dip on the Champlain thrust, which in this case is, it may be up to 1,000 feet below us at the lake shore. But we're starting to see more of these tan-colored dolostone rocks. So the Moncton Formation is, well, it's broadly a sandstone, but there are dolostone layers in it. But if you can see places like in the one quarry at the is the Winooski Exit, you can see an intermingling. So what happens is that the red sandstone layers interlayer with the dolostone layers over about 30 feet. So you just see first little thin tan layers of the Winooski, and then you see it's all Winooski. Yes, and so we're going to get off of the Lake Champlain Islands exit, and so conveniently here we've also come out of the Moncton. We've come basically up again and younger again, and at this exit we're actually going to see more of the cream-colored or tan weathering dolostone of the Winooski that we'll see on both sides of the road. And so here it is. There's the Winooski Formation. Remember, a limestone deposited in a subtropical sea. The dips that are 10 degrees about to the east, 10 to 15 degrees, we're going to go to the left. So one of the things here, if you were to go to the right at this light on Route 2, you're actually going to drive a ways and you'll be in the Moncton Formation, the Winooski Formation, and you'll end with the Dunham Formation. And after that, you won't see any more exposed ledge, and you'll drop down to the causeway going out to South Hero. The causeway is the next slice below the Champlain thrust, and so you will have gone down. Remember the Heinsberg thrust, you went below that at the Williston exit, and then after all our driving here to the west and taking a dogleg to the north, and if you're going to go back west across to the Champlain Islands, by the time you drop down to the Champlain Causeway, you've gone below the Champlain thrust fault onto the next slice below.
So we've just parked here at Chimney Corners, wrapped up the drive from Berlin to Exit 17.
We've gone through a pretty complicated story in 3 dimensions, actually 4 dimensions in time, about how the rock slices between Berlin and Burlington, Colchester were formed, assembled, and modified by erosion over geologic time. We added that the glaciations were the last 1.8 million years of the 550 million year old time scale that we used along this driving transect, and what effect that those processes over that short period of time had on modifying the landscape, making deep glacial lakes, forming structures like Camel's Hump, where one side's gently sloping to the north and the south is steep because the glacier tore off pieces as it moved south. But one of the things we didn't really talk about is that although this is really spectacular to most people with any interest in science, is that we use all the data sets that we talked about for this whole drive. For example, Julia has been working with me on groundwater contamination projects. And what we've had to do is, if you think about the big ledges that you looked at, we need to actually unravel what are all the different cracks and beds and foliations in each in 3 dimensions, so we can actually understand how groundwater and contaminants would move through them. So although it doesn't sound like you would be able to get that out of this, it's a critical part of what we do, understanding bedrock and understanding the glacial deposits and how groundwater and contaminants move through them. Another current project is looking at landslides and rock slides and trying to see their change over time and assess whether there's still risks or not. And for the rock slides, it's a similar thing in that we look at the cracks and the beds and everything and how they intersect and how that can form blocks that fall as very large pieces, either individually or a series of pieces, or glacial deposits that have planes in them that are planes of weakness in this softer sediment and can form landslides that can be 12 or more acres in size and slide hundreds of feet over or day or less. And all these geologic principles that we're talking about are integrated to produce this type of analysis that we have to do. And all of the projects that we're involved with are very complex. And we need a team of geologists of all different disciplines to work together on these problems. And so that's what we've been doing, is we work with other state geologists, we work with academic geologists and students, and we work with federal geologists to try and solve this. And the information we showed you overall is integrated into the analysis that we do for these other projects. Okay. So just as an index, the new state bedrock geologic map of Vermont came out in 2011. It had editors of Nick Radcliffe from the USGS, Rolf Stanley from University of Vermont, Marjorie Gale from the Vermont Geological Survey, Peter Thompson from University of New Hampshire, and Greg Walsh from the USGS. They're editors, and then there were actually probably 100 geologists over more than 30 years that contributed their mapping to this overall compilation. And this is obviously it's a beautiful map. It's 9 feet tall, if you happen to have 9 feet of wall space, and it's incredibly complex. But you also have to treat this as a work in progress, and that there are places that we will map in the future, and then we will add that information to them, to these maps. But this map is used by geologists, hydrogeologists all over the state of Vermont government. It's used by consultants. It's used by geologists at the federal level. It's used by academic geologists and students. And so this is an example of an effort by, again, multiple parties to build a map or to try and understand something complex.
This map and many other maps are available from the Geological Survey website. As digital PDFs are all free, or you can purchase the 9 foot tall map on our website as well. But all of our publications are available for free on our website.
And we encourage you to look at our website to see how we've used geologic information to solve environmental problems.